Morning, everyone. Getting started and hopefully getting to the end of this chapter today. The first reminder is, as you expect, it's all about labs. Today is 8. 2 more days to go. Sunday is deadline and deadline forever. And if you ask me with all kinds of excuses, I will receive it but 50% less. If that is okay, then fine. Please remember, you have to pay the penalty for missing the deadline. So avoid all these little things and go ahead and get it done as quickly as possible. Lab deadline. 10:10. I know. Okay? Just a reminder. The second reminder is I'm going to open the quiz later today, maybe in the afternoon. Quiz 1. Basically, we call it progress test. Okay? I think fair enough. If you have any questions, you can ask me. Now tell me where we were. Net connection is unstable. All right. Morning shows the day. There's the first message I get in the morning. My internet connection is unstable. What a start. Anyways, the other thing that you'll have to do is now you will have to remind me. Anyone?
I think we finished the implementation issue.
I'm sure we were on this page. Should we get started with segmentation?
Yeah, we gotta start with that.
Anyone can give me the lead? Yes, implementation issue. Sure. So can you tell me where exactly in the implementation issue? Oh, policy and mechanism. Separation. Good. Okay, good. Thank you. So we'll get started from there. So we quickly move down. These issues, as we discussed before, were really very important. So let's go down and check them. This is what we were doing. And in fact, I'll give you a quick heads up. It's kind of like remembering what we studied in the last class. What we mean by separation of policy and mechanism and how that thing becomes important in this context. Well, that thing does become important. That indeed becomes an important issue because, as we'll see, that it all comes down to how it is handled. Okay. How the things were handled. Why we call it separation is all about handling of your page fault issue. Now, the best way to handle this page fault issue, as we understand, is by separating this mechanism from the policy implementation. In fact, there were three different layers, okay? Three different layers of codes that were collectively taking charge and cooperating with each other to resolve these page fault related issues. The first one, the topmost, that was running in the user space, was what we called, if you can still remember, external pager. Remember these names. The second one, it is in the kernel, and that is the one that basically controls much of the mechanism. So external pager is all about implementation of policy. I'm writing that part. It's all about implementation of policy. But the kernel is the one where we have a module, and this module is called page fault handler, if you can, or simply fault handler. I can't write it. Fault handler, and this fault handler will be responsible for the implementation for the much of the mechanisms that we have. And finally, at the bottom level of kernel, close to the machine, we have a machine level code that is called Mmu Handler. This is the one that will handle Mmu, that will present the actual page to the handler, to the Mmu, and Mmu will generate the logical address. Okay, that is what we are doing. So that is the one that we understood, and how it all worked. It all worked in a way that, as you can see, that It all started working right from the top level, the user level, where the user process was running, and it generated a fault. As it generates a fault, that means basically a trap to the kernel. We know it. The kernel is alerted. It's a trap to the kernel, and kernel is alerted. And that kernel, what the kernel will do is, of course, the first thing they do is to save everything. Save the registers, save the PC, especially PC. And then from there, the fault handler steps in. Fault handler will take the virtual address. From the virtual address, it will figure out, from the virtual address, it will figure out the page number that is missing, the page that is missing. And then it will get in touch with the external pager, asking it to find the page on the disk. Now, it's the external pager's job to initiate these I/O. Okay, this is an I/O, as we already always mentioned. So this is an I/O. So we have an I/O initiated. And when the page arrives, it should be copied to the external pager's own address space. And then external pager will ask page fault handler to get the code. The fault handler will simply unmap it from the external pager's address space, hand it over to the MMU, and MMU handler will send the page address to the MMU, and MMU will generate the physical address. And it's the MMU handler that will finally put it in the address space of the user process. This is the user process in its address space. This will be the page that is coming will be placed there. Okay. Only after that, so some problems with this one. Only after that, this one will be restarted. The process will be rescheduled, and the CPU, the PC will be reset, and it will start working again. So that is how we managed this, what we call the page fault handling. I haven't. Still can't write. Wait a minute. For some reason, this. So that will bring us to the next part. That is what we call segmentation. Okay. And this is going to be one interesting part, segmentation. So first of all, why do we have to think about segmentation? Of course, earlier we saw a little bit of the same thing being played out. Okay. The segmentation. And how do we do that? The way we deal with it is the way we do the segmentation, the way we apply segmentation is there are a few reasons behind it. Well, first of all, and I think this is one of the most important things here to consider, that when we think about the segmentation, when we think what was happening before segmentation, we will clearly understand the problems that we are referring to. For some reason I can't write it here. I'll be needing that space. All right, wait a minute. I need to Still can't use it. Sometimes I don't know what happens. Anyway. All right. Seems I still can't. Oh, okay, fine. Now, so what we want to do is understand what were the problems before segmentation. Now, segmentation, we already had a little bit of an experience of segmentation, and we didn't use a word segmentation there because remember in page designing issue, we were talking about shared pages that eventually led us to shared libraries. So basically that was a basic segmentation, only split up in two parts, a data part and the I space. So D space and I space, if you can still remember. Now, what was happening before segmentation was that you were writing the programs in this way. And that's the way we write the program. So basically, if you're working with Java, for example, you have a whole bunch of class files and the dependencies and maybe the source data file, and then this Java archive files, the jar files, an environment, a project environment. So that is how you visualize or see or conceptualize your program, you and me as a programmer. So basically for us, it is at least two-dimensional, if not three-dimensional. It is two-dimensional, okay? Everything is separate, separate, separate. But the entire program, when it is presented to CPU, CPU doesn't look at it in a two-dimensional way. For CPU, it's a very straight, linear thing. Linear, one-dimensional thing is just like one single line, and everything sequential, everything sequential. Okay? And that's how it generates the address space 0 to n. Okay? The problem of these is, first of all, we the programmers, when we are writing the programs, we have no perception or no idea exactly how much space our program is going to take while loaded on RAM. Because that doesn't really depend on the volume of codes that we have written or the size of the file. Okay, so it is, as we already know, it's a CPU estimation. Because CPU reads all these files in one single line. So we have no idea. So when we present our program to CPU, and CPU puts everything in a sequential way in one single line, and then it starts generating this address space, which definitely has a limit value, because this M is directly related to RAM. How much RAM is available, and how much and how many addresses the CPU can generate for that RAM. And depending on that many addresses, the maximum value that CPU can afford to generate. So even with address space. And that is where the things were tied to the physical memory. Remember, this is what we discussed before, that it is tied to the physical memory. But now, when it is tied to the physical memory, the problem that we started encountering is if it is the program is assumed to be too large for CPU in a linear way, then CPU will fail to generate the address, logical address, for a part of this program. Try to understand. Because it's trying to generate one single address space. One single address space that must cover the entire length of the program is the program wants to run on that particular machine where you have a limited, restricted amount of RAM. And for that, CPU must generate the address, must cover the entire length of the program through the address space that is from 0, that ranges from 0 to M. Now, if M can't cover some part because M is just too short for this program, it can't be generated. So if it can't be generated, then that program will never run. Okay, because it doesn't have an address space. So how can it run? So naturally, this was the problem that we were facing all the time. Now, what kind of problem it was? First of all, as I said, the program will not run. Okay. So let's write down the problems. The problems were the first, the program, one single address space. So naturally, because of one single address space, the issue is one address space. And because of one address space, large programs can't run, simply because they didn't get their address space. Number two was there was one single linear address space. Number two, that even if the program gets address space, then it must be in a contiguous position. Contiguous allocation on RAM. Okay, we are not talking about the virtualization here. This is milk. So again, for this contiguous memory allocation was a kind of a headache because we had to put everything next to each other. We had to put everything next to each other because there's a single address space. So since there's a single address space, you can suddenly split it up and put half of it right here and half of it right there. That way it doesn't work. Okay. And then on top of that, we had the third problem, which is another major problem, and it actually comes from the contiguous allocation. And the contiguous allocation, the other process that we have, other problem that we had was the data space. The data stack code, all these will always get dumped in one place. So what does it mean? In turn, it means that none of these sectors can actually grow or shrink. Can't grow or shrink in memory. So we have identified three major issues could be more issues. Okay? So first, the larger programs can't run because they can't get enough addresses, logical addresses. Number two, the contiguous allocation. We have to, because one address space, we have to keep in the contiguous allocation. Then finally, number three, that can't grow or shrink in memory. So naturally, these are the three problems that we were encountering. Okay. So how can we deal with this thing? The one way of dealing with this thing is if we can somewhere, remember, this stage we are talking about pure segmentation. How about if we can, even before we present it to the CPU, if somehow we could break it down into multiple sectors or multiple segments. Okay? So if we could do it, then probably we could resolve this issue. Virtual memory, as we see, the virtual memory is a limited value solution to this problem. This is the word that I use. Virtual memory is a limited value solution. Of course, it's a solution, but it doesn't solve too many things because it is still one-dimensional. And of course, only one thing that we do in virtual memory, and we did, was the separation of logical memory from physical memory. So any program can now have, it actually solved only the first problem and perhaps the second problem. But this problem is still unaddressed because all the pages are of same size. So that was still a difficult proposition. So what we are trying to achieve is segmentation. What we're trying to do is segmentation. And what is segmentation? So what we are going to do is segmentation. So what do? We need to, even before we place it, or before we hand it over to the CPU for further addressing or address spacing, we want to split up our program into a logical segments. Now, split it up into logical segments. This is an important concept. Now, if you want to split it up into logical concepts, then you need someone to read the code. You need someone to read your code, right? But who will do that? Who reads your code? Okay. Of course, the operating system and the CPU, none of them will read your codes. But you need someone to read your codes so that they can apply a logical division of different parts of your code depending on what or how, it depends on how different parts going to behave on RAM. Okay? Basically, what they are for and what they do in the program. So these are the parameters based on which we will use logical segmentation. So this logical segmentation, once we do the logical segmentation, then definitely there is a benefit. What are the benefits? Let's take a quick look at the benefits. So what happens now is, previously this was your program and you had one single linear address space. Now the program, before it is presented to CPU, is already split up into segments. Altogether, this is your program. And now CPU will generate address space, separate address spaces, of course still linear, but separate address spaces for individual segments of your program. So think about it. So think about the first problem that we talked about, because of one single linear address space. That some of the larger programs couldn't get any address space. Okay? So, but in this case, now that won't be a problem that can easily be covered. Okay? So that will be one of the key benefits. Each part of a program, however large they are, if they fall in a separate segment, they can easily be covered by the address. So that is what we were doing. So that is the first benefit that we get. It's definitely the first benefit. And then what is the second benefit that we get? Now that we have split them up into multiple address spaces, each of these segments can now be loaded separate parts of the RAM. They don't have to be in the contiguous position. Remember the problem number 2 that we identified earlier? That was all happening because it was right in the contiguous. Everything was in one single linear address space. Now that we have split it up, we can, as you see on the picture itself, we can put them into different parts. And each of them will have their own, as expected, own base value and limit value. No problem, depending on their separate address spaces. So each of them will have their base value and the limit value, which is B plus L. So this is one segment. They're part of the same program. This is another segment. This is another segment. This is another segment. But they're disjoint. That means they are not in contiguous position anymore. There's absolutely no need, because each of them, they have their own individual address space, an independent address space, separate address space. That is the key benefit of this thing. So there we are. Now your program looks very much like this. And as I said later on, when we go towards the end, what we will see is, remember what I said, that memory management will come down to logical interpretation of logical interpretation of logical interpretation of your program. 3 layers of logical implementation, a logical interpretation or logical mapping on your program. So I once mentioned it. So logic and logic and logic. What I'm talking about is, first, logical segmentation. This is your program. Okay? Logical segmentation. First, you do the segmentation, logical segmentation. And that is the first thing that you do. That is segmentation. Each segment will be handed over to CPU individually, and they will be logically address space, because address space itself is logical addressing, okay, for each line of codes. That will be address space. Once the address space has been generated for individual segments, now paging, that OS will jump in and we apply paging, making equal sized logical clusters of chunks of address space. And we know it. But for the time being right here, we will not talk about it. Here we are talking about pure segmentation, and afterwards we'll talk about segmentation with paging. Okay, that too is very interesting. So we will have OS who will jump in to apply paging. So that is what it is. Now the important point here is how will you refer to an address? We understand the benefits. The third benefit we didn't talk about. The third benefit is now that since they are totally separate on RAM, they can grow and shrink because CPU knows, the OS knows exactly who does what. So based on that, some of those, for example, the codes, they don't need extra space, but the data that belong to the data space or a table, for example, is another segment. So the table segment will be allowed to grow on memory. Okay. So this is the most important part. And also sharing of codes will be facilitated. So we can easily share the codes. And now, how do you address it? Well, you have it. You have the segment number. Okay. And an offset. Segment number means this, which segment you're referring to, and the offset means this. Inside that is the logical address. It's same, like we always use the offset, and it does change. It doesn't change because everything has to come down to that logical address anyway, because CPU, that's the one thing CPU understands. So naturally, that 4K that you're looking at right here will be the offset. So we have segment number and we have offset. And we maintain for each program, we have what we call a segment table. What do we store in segment table is very interesting. The segment number, 1, 2, 3, 4, 5. Its limit value, first the limit, so I say limit. For example, this segment, so segment 2, the limit, segment 3's limit is 16K. Right? And the base value where on RAM or physical memory it is located during the runtime. So we have a segment table. And how do we calculate the physical memory of any address, any line of code, any address from any segment? The calculation is very simple. We'll see it right here and then we'll move back. See what they're talking about. How do we do it? So we have a segment number and an offset, and we also maintain the segment base and the segment limit. So the calculation now is pretty easy. The first thing that will be checked is that with the segment number, you know exactly where on the table which segment you're referring to. So you, by using the segment number as an index, you pick up that particular entry into the segment table. And for that particular entry, you check the offset, whether it is greater than limit or not. If it is greater than limit, then there will be yes, fault. That means this address that's trying to access doesn't fall inside that segment. It's usually generates a segment 4. If it is no, then find the physical memory as base plus offset. Try to understand it logic, simple logic. That's exactly what they're doing. Segment number, D is the offset. With the segment number, using the segment number here as an index, you find the entry of the segment table. This is the segment table. First, check the limit value. The D is less than limit. If it is yes, then take the D, the offset, and add it with the base and find the physical address. Okay? Otherwise, there will be a trap and addressing error. Now, the whole that part we understand. Now, the next big question that comes up is that who will do this? Who will do the segmentation? We are talking about segmentation as a wonderful idea, novel idea that will be split up into different parts, and CPU will generate a whole bunch of address spaces, whole bunch of address spaces. So that is one of the good things that we have right there. But the question still remains that who will do it? Who do you think could be a good candidate for this segmentation job? Obviously, we need someone who reads the code. And who reads your code? Your compiler. Yes, your compiler. Now, when you are compiling your program, that compiler will read the code and will apply segmentation. And you can see it right there. Okay? The compiler automatically constructs segments reflecting the input code. So since it is the compiler that will apply this technique of segmentation, you as a programmer, you too will have to shoulder the responsibility. You too have certain responsibilities. Now, what is your responsibility? Your responsibility is to organize your codes and put them in the right format in such a way that your compiler can easily apply segmentation on your codes during the compilation time. So you also have a certain responsibility. In some old-fashioned procedural languages, we had to literally add those annotations to tell compiler that what we are intending to do in that part. So basically, the compiler knows how to apply segmentation. Okay. But now in modern times, that is one of the biggest headache, of course. I mean, you are a programmer, your entire focus is on logic, okay, and codes and algorithms, and now you have the extra responsibility of figuring out that what to write, all these bunch of annotations. And these annotations we had to write. I mean, this was the industry standard even a few years ago when we were stepping into the job market. We were taught to write a whole bunch of annotations in your program. But if you write 5 lines of codes, you probably end up writing lots of annotations. So not everything was for the compiler, but structuring your codes in the proper way is your responsibility, because you have to guide the compiler. You have to guide the compiler so that the compiler knows exactly which parts should be put into which segments. And this is a huge, huge headache, sort of. And now you understand that why, to relieve you of these unnecessary headaches, we have now, for all the modern languages, we have introduced the concept, and that concept is of IDE. Now, for all these languages these days, you have an IDE. IDE stands for Integrated Development Environment, right? If you go for Java, you have your NetBeans, you have your Eclipse, and in fact, all programming languages now are supported by an IDE. So IDE basically helps in a lot of other ways as well. But one of the benefits that you get from IDE is that it helps you to stay on the right track. To stay on the right track means that it kind of controls you from making things a bit messy for compiler. You have to write things in a certain way, because if you don't write things in a certain way, when you are writing your codes in real time, the IDE is checking your codes. You go to the next line or the next word, the word that you typed before will be marked red, because it has already been checked and is found to be an error. So whatever, there's a mistake there. That kind of control, and also you know that sometimes in the IDE, they add the annotations on their own. So we use the IDEs because one of the reasons is that it reduces the extra responsibility on the programmer side when it comes to segmentation. But anyway, we understand that compiler is the one who will apply segmentation. We will see the benefits of it, and we know how to calculate. There's an example. A quick look at the example. Say, for example, segment 2 begins with 40s, and if a byte of 53 of segment 2 is referenced, where will it go? What will be the physical address? So first, segment 2. Segment 2, limit value 400. Is 53 greater than 400? No. So calculate. What is the starting point? Base value 4300, 4300 plus 53. So the address is 4353. The physical address is 4353. Not difficult. Okay? Stay aware, because these are the questions that you ask. If a byte 1222 of segment 0 is referenced, a byte 1222, okay, of segment 0, limit value 1000. Is it redder? Yes. False. A trap, an addressing fault, not a segment fault. Segment fault happens when that segment is not found to be loaded on RAM at that point of time. Okay, so this will generate an addressing fault. So that means the address that you are trying to refer to doesn't fall in that segment. As simple as that. So what are the advantages? 4 key advantages. Okay, it's now less expensive. So with address 0 as its starting address, when a procedure called to the procedure locating at segment N as N0, no procedure need to be changed. So maintenance, easy maintenance. And number 2, can grow and shrink independently. Number 3 is sharing. And number 4, differential protection. So some segments are more important. So those segments can have a higher level of protection. We'll see it when we talk about Intel Pentium. What is the disadvantage? External fragmentation. This. This is an example. Sharing. This is the example of what happens when it comes to sharing. We already talked about in designing issues, basically. That's it. So editor, both of them, they have the editor part sharing the same I space, and the data space is separate. So the data space must be loaded, but the I space only one time. Okay? And both of them can use the I space from their page here. So that is exactly how they share the data. It's possible, it wasn't possible when we had the paging, but it is possible when we have segmentation. This is one of the most important slides. Now, if you look at it, this slide, you'll understand why I say that paging or virtual memory management is a limited value solution. The best solution is definitely segmentation. The only difficulty is this one. Need the programmer be aware that this technique is being used? Yes, because it will be done by compiler. So the organizer, the programmer needs to put them in the right format. Arrange codes. Okay. Whereas in paging, no. And this definitely can give you a lot of headache. That's an extra responsibility for a programmer. So to help you with that, we have IDE. So you don't have to worry about formatting. IDE will do it. Then now that it is gone, what else? How many linear address spaces? Still one. But there we have many. Can the total address space exceed the size of physical memory? Yes and yes. Right? But they do it in a different way. They are in a still and linear way by generating virtual addresses, virtual pages. And this is done by using diff separating the segments. Can procedures and data be distinguished and separately protected? No. Yes. Can tables whose size fluctuates be accumulated easily? No. Yes. That's where the value goes up. Is sharing of procedures between users facilitated? No. Yes. So why was it done in the first place? To get a large linear address space without having to buy more physical memory, a physical RAM. That was it. To allow programs and data to be broken up into logically independent address spaces and aid sharing the protection with higher values. So now that we understand, if we compare this one with that one, we understand where we stand. Then we move on to see the problem with segmentation. The problem with segmentation, as we said, is external fragmentation or checkerboarding. Please remember this name. Basically, it looks like a checkerboard, isn't it? Kind of like chessboard that you play. You have chessboard, checkerboards. All of them are chessboards. You have the game. You play set two. That two is a kind of checkerboard. So how do we address this checkerboarding issue? Well, the all these fragments. But that is an expensive solution. You can't always do it. And it happens because of one single reason. Okay, for pure segmentation, this is one of the major flaws. Checkerboarding happens because this particular, the segments that we are dealing with, the segments are not of equal size. The segments are not of equal size. And fragmentation is one thing that we never mentioned when we were in virtual memory management. We were dealing with paging. And why was it? It was because in virtual memory management, in paging, all the page frames and all the pages were of the same size. So there is no question of creating a fragment. A fragment, in terms of a page frame, can easily accommodate a loose page from any program. And these pages can fly in and fly out and go anywhere. So we didn't have that problem. But here the problem, pure segmentation, comes back. So we start thinking about, why don't we combine these two things together? Why don't we combine these two things together? To combine these two things together, we have to combine the advantages of segmentation. We want to combine the advantage of segmentation with paging. That is what we want to do. So that is how we do. So paging, the segmentation. To apply it, and that is exactly that way we will get the advantage of it. So what we are proposing exactly is that just now we talked about the problem. Okay? How about each of these segments are paged out? So basically we don't want to keep the entire segment. So basically right now we are putting in the whole segment, right? And that created this checkerboarding problem. So we don't have to load the entire segment. Part of the segment will come and go. All right? So that is the technique that we are going to apply. It will give us the benefits from both sides. That is exactly what is done in Intel Pentium and in Multics. We will see how it is handled. In Intel Pentium, they maintain to this. Remember, just now we said that we had a table, that segment table, but here they have two tables, or two types of tables, a local descriptive table and global descriptive table. They call it the descriptor, LDT and GDT. The virtual address that is inside, each program has its own LDT, but there is a single GDT shared by all programs on the computer. Now, inside the LDT, we have the virtual address that is presented is a collection of selector and offset. Now remember, over there, we had page index and offset. Now here, they call it selector and descriptor. So don't get confused. The names are different, but the mechanism is still the same. What we have inside the selector part is it's a 16-bit number. The first 13-bit is basically the segment number. Specify the LDT or the GDT entry number, which is basically telling you this is doing the same job with the segment number. So you can say that these were synonymous to what we already learned in terms of segment number. That will point at its entry. Okay? Will be used as an index inside the LDT. 1 bit tells whether the segment is local or global, and 2 bits for protection. The offset part is 32-bit number. Is a 32-bit number. And the offset we don't have to touch. The offset will stay as it is. So when this virtual address is getting converted, and it is the one that we have in the 32-bit register. How the conversion takes place, that is the most important part. When it comes to the conversion, again, we have a collection of selector and offset. And a part of the selector, by using that part, the 13-bit part of the selector, you can find out where exactly in the descriptor table, where exactly that particular base and limit is entered. So let me draw one more. This is the descriptor table, maybe LDT. Okay, in LDT, you have some indexing, limit, and base. And this is the index. Now this index number is coming from the initial 13 bits of selector. Remember, selector is a 16-bit number, 13, 1, 2, 1 for GDT or LDT, 2 for protection, and 13-bit will point at the segment number or the part where the entry number, which will be used as an index into this LDT or GDT, in the LDT. So we get the limit value. So by using the selector, we can find out that which particular segment we are dealing with. And again, the same thing, compare it with the limit. If it is within the limit, then add the base plus the 32-bit offset, and you generate a 32-bit linear, 32-bit linear address. We call it a linear address. Remember this one, 32-bit linear address. Okay. Now, once you have generated the 32-bit linear address, then comes the trick. If you stick to only, this is called the linear address, that is the most important thing. So once you have this linear address, then you move on, you have two options. If you choose to apply, not to apply paging, then these linear address will be taken as the physical address. This linear address will be considered as the physical address on the memory. If on the other hand, now you decide to apply paging, and in fact multi-level paging, then of course the things will work in a slightly different way, because the linear address that you have generated, this linear address will be considered as the virtual address. And from that virtual address, applying multi-level page table, virtual address and mapped onto the physical address by using page tables, it will have a directory divided into three parts: directory entry, index into the page directory to locate the pointer to the proper page table, and then from the page table you get the page index into the page table to find the physical address of the page frame. So it's a technique, it's a multi-level page entry. So basically it's a 32-bit number. Right. So the first part will tell you a directory, just like a directory entry. Directory entry means it is an entry for it. It is also a page table, but in this page table, these indexes refer to other page tables. So you find out first which page table you have to go to, and then once you get to the right page table, then you get the page number, and once you get the page number, you get the page frame, and once you get the page frame, you add the offset to it, and you find the physical address. And that is what happens when you apply paging on top of that. Please remember these things. These are important, very important for your exam. These two, especially the segmentation and how they do it how they apply segmentation with or without paging in Intel Pentium. Protection level. As we said that we can actually apply different levels of protection. So there are in Intel Pentium, we have 4 levels of protections, and these 4 levels of protections are applied progressively, and we have some access-related privileges and restrictions. The highest protected one, that means the one with the highest level of protection, can always go down. Just level 3 can always go to access the lowest level. If 0, level 0 to high. Kernel of OS handles I/O, memory management, other critical matters. The system call handler is present, contains library procedures and user programs. So basically, the highest one is the 0. In fact, it is putting it down. Okay, that is the highest one. Highest level. And this is the lowest level. All right, so what does it mean? The highest level easily can access the lowest level. The program is itself using segments of its own level. That's true. Attempts to access data at higher levels are permitted. Attempts to access data at a lower level are illegal and will cause traps. To call procedures, the different levels are allowed, but in carefully controlled way. Okay, so the attempts to access data at the lower level, well, that is what they call the lower level, because this level is 0. That means this is the highest protection. Don't confuse. This is the lowest protection. Lowest protection has the maximum value, or higher level. That is what we call. So user program, a kernel can access user program, but a user program is not allowed to access something from kernel. It is, if you want to understand in an algorithmic way, think about Mr. CEO. The kernel is the CEO. In his office, there are lots of important things, important documents. And here's the lowest level protection, or with the highest value, that is 3 at this level. This is the security guy working in the office. Well, he has limited access. He is not allowed to go there, step in whenever he wants into the CEO's office and look at his papers. Okay? And this access to the CEO's office is very much controlled, because there is the most vital papers, the important information and papers are right in there. So naturally, that is how they apply the different levels. You just try to remember these parts in whichever way it is easier for you. Finally, we talk about multiplexed. Multiplexed information computer service was very popular in early days, We call them multics. Okay, extraordinarily inferential early time sharing systems. So each program has a segment table with one descriptor or segment. And the segment table is itself a segment and is paged. The segment table itself is paged. The descriptor contains an indication of whether the segment is in the main memory or not. If so, the segment and the page tables are in memory, then it will go ahead, and how will they continue to calculate? Now that is again another calculation. An address consists of two parts. The segment one is the segment. The segment that we are talking about right here is the address consists of two parts. One is the segment. The address within the segment is divided into two parts, the page number and the offset. So the page number that we have is basically the first part, the address within the segment, and then the offset within the page. So we have the segment number, we have the page number, and we have the offset within the page itself. Okay. In implementation, the descriptor segment is itself paged and has been omitted. So the way it basically works is, and as we said, the segment part is one part. In implementation, the descriptor segment is itself paged and has been omitted. So naturally, by using the segment table, what we get, the segment number is used to check if the segment table is in memory or not. If so, the segment table is located. The page number is used to check if the virtual page is mapped. Is a valid thing or not. If so, the page frame is added to the offset to give the physical address. Otherwise, a page fault is triggered. If not, then the segment fault will occur. If there's a protection violation, then a fault or the trap will occur. So basically, this is a very simple algorithm that you're looking at. In fact, multics came before the Intel Pentium was introduced. So naturally, multics kept it in a very simple way. First, the segment number is used to check if the segment table is in memory or not. If so, the segment table is located. The page number is used to check if the virtual page is mapped. If so, the page frame is added to the offset to give the physical address. Otherwise, there will be a page fault is triggered. If not, then segment fault will occur. If there is a protection violation, a fault or a trap will occur. So step by step. Okay. Basically, if you once you get the page number, then you can usually map the page frame and the physical address. If you can't do it, then there will be a page fault. If you can't find the segment, if the segment is currently not loaded, then there will be a segment fault. If there is a protection violation, then there will be a trap. Okay. So basically there could be multiple issues. So that is what we understand about multics. Multics is not usually in your exam, you may not get this question from multics, but except this part is an algorithm that sometimes they do ask questions from this part. So make sure you understand and keep track of this little part. Then finally, what does TLB do? So basically, during the implementation of multics, we used to use the TLB. When an address is presented to the computer, the addressing first checks to see if the virtual address is in the TLB. If so, it gets the page frame number directly from the TLB and forms the actual address of the referenced word without having to look in the descriptor segment or page table. Otherwise, the descriptor and the page tables are referenced to find the page frame address. Then the TLB is updated to include this page using aging page replacement algorithm. That's okay. But the things to remember from this part, this one, that's enough for multics. But Intel Pentium is important. They do as in, especially the protection levels of Intel Pentium. The conversion, this is an important slide, in both ways. In pure segmentation and when you apply paging on segmentation. Selector, descriptor, okay. The selector is a 16-bit number, and 13 bits specify the LDT or GDT entry number. Bit tells whether the segment is local or global. 2 bits relate connection with value and the 2-bit number. So this, and also apart from that, some of the very basic things that we learned about how do you find out the real address in theory, not in Intel Pentium environment, but in plain theory, theoretically, how do we calculate the value, the physical memory from the virtual address that we get. Paging the segmentation. We learned all about these things. And this chart, very important. So in general, segmentation part is important and interesting, as you can see. And I strongly recommend that you go there and you study it a little bit on your own. Okay. So that brings us to the end of this particular chapter, memory management, the long one, as I said. It took 2 weeks exactly. We will start with a new chapter, but in the meantime, don't forget to take your quiz. I already gave you the password, 12345. Remember, you can do it only one time. So do it only when you feel absolutely confident that yes, you can do it. Let me check your attendance. Xuan Huang, Ji Kang, Ji Kang, Vin Phuc, Vin Phuc, Trực Huang,
Yes, teacher.
Luang Ha,
Yes.
Hu Huang,
Yes.
Tan Hung,
Yes.
Tan Hung,
Yes.
Nop Phat,
Yes.
Din Min,
Yes.
Guo Phui,
Yes.
Yan,
Yes.
Yan,
Yes.
Kim Tak,
Yes.
Kim Tak, Nhật Min,
Yes.
Min,
Yes.
Tien Phuc,
Yes.
Wang Hui,
Yes.
and Min Kuang, Min Kuang, Huy Bao,
Yes.
Wei Min, Jen Liam Chuk,
Yes. Yes.
Guoc Hum,
Yes.
Ji Kang is getting vaccinated. Okay, on consideration, I get. You won't do it?
Yes.
All right, that's all. And don't forget your lab. That's the most important thing. And we'll see you again on Monday.